All right. So hello everyone. So I'm Shen, and welcome to the session Machine Learning Security. And let's welcome the speaker Linkang from Zhejiang University. He will present the first paper, ORL-AUDITOR, Dataset Auditing in Offline Deep Reinforcement Learning. The stage is yours.
Thanks for the introduction, and this is my first second paper about copyright auditing. And in the first day, we present the copyright auditing for the text-to-image model, and this one is for the offline deep reinforcement learning. And I'm Linkang from Zhejiang University, and today I'm going to present our recent work for the dataset copyright auditing, and which is joint work by Zhejiang University, Stanford University, and the CISPA. And many thanks to my co-authors. Oh, this does work? Yeah. As a popular paradigm of machine learning, the deep reinforcement learning has been successfully applied to many complex tasks such as robotic control and autopilot. The key idea of the deep reinforcement learning is to learn the optimal policy from the interaction with the environment. And the right is a quick example. The kit is it's a GIF, but the PDF field does play the GIF. So it's a picture now. The kit gets the food from the plate and the rings bell and gets the food. And after several rounds, they learn the behavior policy that rings the bell and gets the food. And the kitties are usually called agents in IL scenarios. They feel hungry and observe there's no food on their plate. And after that, they ring the bell and get the reward. That's their food. That's finally they get the policies as how to get the food. Yeah. However, for safety critical domains such as robotic control and the power system, directly interacting with the environment is unsafe since the particular policy may risk damage to the hardwares. To address these issues, the research from the offline DIO models that learn from the pre-collected data from the expert or the handcrafted controller. To facilitate the research of offline DIO, several high-quality datasets are published, but the public data with strict open source license, they are still at risk of potential misuse and infringement. The defense against the above threats comes to the question that how a data owner can prove the suspicious model trained on their datasets. Here is a figure illustrates the typical application scenarios. An adversary with access to the datasets illegally builds a private model. Institution 1 does the first institution. Suspects the model are generated by their datasets, and thus here an auditor to check whether the suspect model use their datasets. And during the auditing, we assume the auditor has full knowledge of the target of the dataset being audited. That's the target datasets, and the auditing without any auxiliary datasets. And we consider the most general and challenging scenario, that the auditor only has the black box access to the suspect model. And there is some existing solutions appear to solve the problem, such as watermarking-based methods inject the samples of specific distribution before publishing the datasets. However, since open source datasets are already published, and the auditor needs to post the event mechanism that does not require inject and manipulate sample before publishing the datasets. Also, the watermark are inflexible to be adjusted after the injection. And the second way is the dataset inference or the membership inference. The core idea is to leverage the dataset's inherent and unique features as in the fingerprint. This enthusiastic feature can be detected in models' behavior trained with datasets and can serve as the evidence of usage. However, the distribution of the offline I/O datasets not only depends on the environment, but also the strategy interacting with the environment. Thus, it's challenging to find proper auxiliary datasets in offline I/O scenarios. Additionally, the inference strategy usually embeds the classification task that are not easily to be migrated to the I/O scenarios. And here we show the behavioral similarity of offline I/O models trained on different datasets by the L1 norm. The dataset 0841 is a target dataset, and the other four datasets on the axis are the auxiliary datasets. We observe that the behavioral similarity of the I/O models weighs heavily among the different auxiliary datasets. If the auditor adopts the first dataset as the auxiliary datasets, and the other three auxiliary datasets are classified into the positive results, that the model was illegally traced on the target test, but we also know it's misclassified. And the existing dataset inference or the memory inference behave poorly in I/O cases. On one hand, lack of auxiliary datasets limits the performance of the algorithm, and in addition, it's improper to directly use the action of I/O models as the auditing basis. And we are inspired by the fact that the rewards getting the I/O models to learn the behavior policy. Thus, the reward is an enthusiastic feature of the datasets, and as a suitable auditing basis. This figure provides the institution of our proposal, where the state action and the cumulative rewards compose a three-dimensional space. The mid-surface illustrates the exact cumulative rewards of the datasets, and the other two surfaces show the possible offsets of the DI models learned the cumulative rewards, since the randomness in the initialization and the learning process. And for the suspicious model, the auditor output positive results if the cumulative rewards lies in the two boundaries, and otherwise a negative outcome if the out of the boundaries. From the illustration, the well-designed function Q and the boundary delta guaranteeing the effectiveness of our proposal. And Go details the whole workflow of our proposal contains the three steps. And in the first step, we leverage creative model to serve as the auditing basis and predict the cumulative rewards of the state action pairs of the I/O models. For the auditing boundary delta, we utilize the shadow model idea that popular in previous works, and where we train the multiple model on the target dataset with varying initialization and optimizations, and they collect the cumulative rewards of their state action pairs. And in the second step, use the critic trained in the first step. The auditor calculates the estimate cumulative rewards for all state action records of the shadow models. Then the auditor queries the suspicious model that in the bottom of the figure with the state and observe the suspicious model's action. The state action pairs are then put into the critical model and obtain the estimate cumulative rewards for the suspicious model. Then we come to the step 3. And by comparing the cumulative rewards from the suspicious model and the shadow model, and we make the auditing decision by hypothesis testing. Okay. In the evaluation, we adopt Lunar bed pedal work and task in GIM, which are widely used in previous works. The tasks stem from distinct real-world problems, each with numerical vectors contain different physical information, such as the position, the velocity, and acceleration. These tasks involve both discrete and continuous variable in observation and action, and their dimension range from the low to high, from 2 dimension and to 111 dimension. And for ease of reproducing our environment, we provide all used random seed and Python scripts. This figure summarizes the whole process, and the online and offline models are implemented by offline IOs, open source IOs libraries with default settings. And we assess the effectiveness of our proposal across 12 combinations of three tasks and 4 different IO frameworks. And most true positive rates and true negative rates are higher than 95%, meaning our proposal is a valid solution to audit the learned datasets of the offline DIO models. Okay. And to further explain the audit results, we analyze the cumulative rewards from the shadow model and the suspect model by Tisney. And in each figure, we show the results of 3 trajectories from the target datasets. The 30 positive point for each trajectory are collected from the model trained on the target datasets, and the 30 negative points are trained on other datasets. And for a trajectory of the target datasets, the cumulative rewards of the shadow model and the suspect model are clearly divided into different groups. This means the cumulative rewards will reflect the behavior difference between the different models. And we also extend our assessment to 3 pivotal factors that impact the effectiveness of our proposal. And we consider the amount of shadow model and the significance level in hypothesis testing and the length of trajectory. I will not go into the details here, and so please refer to our paper for the experimental results and the corresponding analysis. And to handle the auditing, an adversary may utilize the SOTA defense strategy proposed in recent work, such as the Istanbul learning and the action distortion. This defense strategy aims to mitigate the influence of the samples on the behavior of machine learning models. From the results, even when faced with model ensemble, the auditor maintains a high auditing accuracy. And we also find the combinations of multiple distance can enhance the auditing robustness against the ensemble learning. And the suspicious model may perturb the action, that is their model's outputs, and to conceal their training disinformation. In the evaluation, we use the Gaussian noise with a different standard deviation to represent the 2 levels of distortion. And ORL-AUDITOR can resist the potential action distortion from the suspect model, and especially with the cosine metric. And the ORL-AUDITOR with a single distance face limitations for heavy distortion. That's the sigma equals to 0.1. Yeah. And in summary, ORL-AUDITOR is the first approach to conduct trajectory level dataset auditing for offline AI models. And we conclude some useful observations for adopt our proposal in practice. And we applied ORL-AUDITOR to audit the model trained on the open source dataset from Google and DeepMind to demonstrate the effectiveness of our proposal. And we also discussed the limitation and the future work in the paper. And in the end, I would like to express my gratitude to my research group. And our research interest lies on unmanned system, IoT and sensing and network and system security. And the following are part of recent publications. And we are hiring, and feel free to visit our homepage for more information. Okay, thank you for your attention. I'm glad to answer questions. Thanks.
All right, let's thank the speaker. So anyone has questions? Come on, we need to give 1 to 2 questions. All right, so maybe I can ask one question. So it seems like during evaluation, so the model owner, so the model owner only use like one data set to train the reinforcement learning model. So what if in reality, if the model owner use like some other data set mixed with the data set consists of multiple data sets. Can you method handle this case?
Okay, thanks to your question. You mean the adversary may mix the data sets from the different organizations? Yes. Okay. The quick answer is no. We don't consider this situation in our paper. But as we showed in the slides, and this the auditor is trajectory level auditing methods. So I think the auditor can handle this situation. But if the audited data is just a very small part of the data set, like maybe the 5% or 10%, I think the auditing performance may degrade. And maybe you can use our open source code to conduct a quick validations of your source. Yeah.
Yeah, and okay. So my second question would be if you can go back to the results, like false positive rate and yeah, the table.
Where is the?
Can we go back?
Go back to the previous slides. It does work. Okay, it's work.
Yeah, so I'm thinking about a situation like because you didn't report like a false positive rate, right? Yeah. So is there a situation that you method like if my data is not being used, but you method consider my data has been used? So it's like false positive rate.
Yeah, I know. It's like the auditor misclassifies the situation. Yes. Yeah. Here we provide the true positive rate and the false true negative rate. But the way we do in the paper, we don't just provide the false positive rate. But I think the true negative rate maybe reflects the situation you consider it. Yeah.
Okay. Yeah. Thank you again.
Oh, thanks.